Welcome to Math Minders Academy. In today's lesson, we are going to look at circle geometry and we are going to explore tangents. So if you are new here, don't forget to like this video and subscribe to this channel for more engaging math content. Let's go. So today in our class, we are going to discuss the definition of a tangent. That is, what is tangent line to a circle? We are going to look at theorems on tangents. We are going to look at the tangent radius relationship or theorem. We are going to look at tangents drawn from a stereo point, and we look at another theorem that deals with the angle between a tangent and a chord, how that relates to the angle in the alternate segment. And at the end of today's lesson, we are going to use a 10-point quiz to test our knowledge. We're going to have 10 multiple choice questions to test how we are able to follow through this discussion. So we urge you to stay tuned and let's dive into this discussion together. Hope you are ready. Let's go. So first, what is a tangent? For us to understand what a tangent is, here I am doing this teaching using a web application that is called GeoGebra. It's an open source web application. I'm going to use it to do a lot of demonstration to show us how beautiful, circle geometry can be when we use this web application to teach it. So first, what is tangent? A tangent is a line that touches a circle at a point. So when we have a circle, all right, this is a circle. Okay. Now, so now we have 2 points. We have the center of this circle labeled A, and we have a point on the circumference of this circle labeled B. And so I'm going to draw a line that will pass through point B, which is on the circumference of this circle, and runs out. This line is not going to run into the circle, and this line is what we refer to as a tangent. So let's look at that. So this is it. So this is what we refer to as a tangent. This line that touches point B and goes off is what we call a tangent. It can touch any point on the circumference, but it must not cut through. Look at this other line here. Can we say this is a tangent? When we have a point, another point on the circumference, let's say point C and point D, and we run a line connecting point C and point D, can we call that line a tangent? The answer is no, because it does not, that line does not pass through a single point. We define a tangent as a line that touches a circle at exactly one point. So we are going to remove this because it does not qualify to be called a tangent. So let's remove this line now. Good. And so the one that is a tangent is this red line. And we have explained the reason why we call it a tangent. It is a tangent because it touches a circle at the point B and does not run through the circle. It just gets to the circle, hits point B, and goes off. That is tangent. So now we are going to look at the relationship between a tangent and a radius. A radius is half of a diameter. It is a line that runs from the center of the circle to the circumference. So now that we have this tangent, of course, this tangent can be moved to any point, any part of this circle. All right. Okay, so now let's move it to this part. Okay. And then let's get a radius. A radius, let's take this line segment and run a line from A to B. Now, this is the radius. So what we want to establish here is what is the angle formed between this radius here, this line AB, and the tangent, the red line. Now, to see that, let's put a point on the red line. Okay, that's point C. And let's check our angle here. Okay, let's check what is the angle formed here when we move from C to B to A. So what angle do you see here? All right. So when we look at angle CBA, it gives us 90 degrees. Okay, it gives us 90 degrees, which we can see here. All right. So we conclude here that the angle between the radius and the tangent is 90 degrees. So we can say the angle between the radius and the tangent, of course, is 90 degrees, which we can see here. So we've demonstrated this. So take note of this. We are going, when we are solving, finding solution to circle geometry problems, we are going to be applying this theorem. Okay, again, we are going to look at the theorem that talks about tangents drawn from an exterior point. And the theorem says that when tangents are drawn from a exterior point, they are equal in length. So we are going to look at that also. All right, so now we look at this circle. All right, let's move this tangent. Okay, we can reduce this. All right. Now let's get another point on this circle so that we can get a second tangent. Okay, so we are going to draw a second tangent to pass through point D. And let's see what that is going to give to us and the point where these two tangents will meet. We draw a second tangent to pass through point D. Okay, so we have the two tangents now drawn. Oh, good. So let's mark off where these two tangents meet. So our external point will be this point E here. That will be our external point. So the theorem is saying that the length DE, so this is what the theorem is saying, and we are going to demonstrate that now. The theorem is saying that this length DE, is equals to length BE. Okay, so we are going to see how true that can be. Let's look at it together. Now, let's take another line from A to D. Okay, so we are going to run a line from A to point E. But don't also forget that we said here before that radius is perpendicular to the tangent. That is, the angle between the radius and the tangent is 90. So that means if I also look at the angle here, let's say angle ADE, it still gives me 90 degrees, right? So we have this. Now, what we want to prove here, we want to prove that this line here and this tangent here, okay, coming from this exterior point, that they are equal in length, okay? So what we are going to do now is the fact that we can establish that these two right angle triangles are actually, in fact, we are going to establish the fact that they are congruent. And let's look at that. So here, you agree with me that angle B is the same thing as angle D, and this is 90 degrees. All right. And then you will find out that we have two right angle triangles here with a common hypotenuse. So the hypotenuse for triangle ADE is AE, and that is also the same hypotenuse for triangle ABE. So here we say that AE is common for both triangle ADE, for both triangle ADE and triangle ABE. Okay, it's a common side. Let me show that very quickly. Look at this hypotenuse here. Let's make it blue. So this blue line here is common for these two right angle triangles, ADE and ABE. So that side, that line is actually common. Okay, so now we're going to look at another thing here. We're going to look at another thing here. Let me remove this. Okay. So now let's see, we also have, now what we want to establish here is the fact that these two triangles are congruent, and if we can establish ROH for congruency, this is what we are looking for, which is a condition. One of the conditions for congruency is ROHX, which is one right angle, one hypotenuse, and one side. Now let's look at another thing. In triangle ADE, AD is the radius. So here we can say that the length of AD is the same as the length of AB. Okay, what is this? We are talking about the radius of the, of course, radius of the circle, irrespective of where it is drawn to us, from the center to any part of the circumference is radius. So from center, which is center A, to a point B on the circumference is a radius. That does not change the size of that radius if it is drawn from the same center A to point D. It doesn't change the value. So here, what have we seen? We've seen two sides that are common to both triangles, which is the side AD and the side AB. And we have also seen that the hypotenuse is common. And we have seen that each of these two triangles have a right angle, which is 90 degrees. So we've successfully established ROHS, meaning that triangle ADE is congruent to triangle ABE. And when two triangles are congruent, what does it mean? It means, therefore, that all the sides, all the corresponding sides are equal. So having demonstrated that these two right angle triangles are congruent, we can say, therefore, DE is equal to BE. So here we have demonstrated that these tangents drawn from external point E are equal in length. Now, this is a very classic demonstration that stands for all. And come to think of it, if we just want to look at some practical example, it is given that the radius is 5, for example, and the hypotenuse is, let's pick a number here now. Okay, let's pick so that we create a Pythagorean triple. Okay, let's demonstrate. Let's give this. Okay, let's give this a value. Okay, let's give this, let's say the radius is 3 units and then the hypotenuse is 5 units. Okay, now for the first triangle, if I am looking for the first triangle, that is triangle ADE, if I am looking for the length DE using Pythagoras, the length DE is going to give me, using Pythagoras, I'm going to have DE squared is going to give me 5 squared minus 3 squared. Okay, that's going to give me 25 minus 9, and that's going to give me 16. And so when I take the square root of both sides, that's going to give me square root of 16, and I have 4 units. Okay, now because the radius is the same irrespective of where it is drawn to, as much as we are drawing from the center to any part of the circumference. So if I also draw from A to B, this is going to be 3. For triangle ABE, I get 3. And this blue line is still the hypotenuse of this triangle ABE. So if I am looking for the side BE, using Pythagoras also, the side BE, how do I find it? It's going to be BE, that's the square of the hypotenuse minus the square of this opposite, and that gives me 25 again minus 9. This gives me 16, and so BE here is going to give me square root of 16, and that gives me 4 units as usual, just as I got here, and that's the same thing. So we've seen, a practical demonstration that tangent drawn from external points are equal in length. Hope that makes sense. We're going to proceed now to look at another theorem on tangent. This will deal with the angle between the tangent and the chord. Let's proceed. So the next theorem is the alternate segment theorem. So let's remove everything that we have here. I will look at that theorem together. Okay, so now let me also remove this circle. I will demonstrate with another one. Okay, so now let's draw a new circle, and then we have this. Okay, that's center. The center is center A. If you also wish to, you can change that center to center O, which is usually the conventional way of depicting the center, of a geometrical object. So that, and now we have a point here. Now, let's try to draw a chord. And a chord is a line that connects 2 points on the circumference of a circle but does not pass through the center. That's a chord. So we need a second point which on the circumference of a circle, let's say that's point A. And now let's join A and B together, okay, using this. Okay, so that is done. So we have this, okay, okay, that's beautiful. Now, you will observe something here, that the chord AB has actually divided this circle into what we call segment. So we have this part of the circle that is cut off by the chord is called a segment, a minor segment or a smaller segment, right? And then this part that is unshaded, the larger part of the circle that is cut off by chord AB is called the major segment. So the chord actually divides this whole circle into two segments. Now we are going to draw a tangent. We're going to draw a tangent. Let's say we want the tangent to pass through. Okay, good. So let's pick our tangent to pass through point B. Okay, now I'm not going to make any attempt to prove this theorem because that's the scariest part, of the circle geometry concept to students, because of course for the audience that this video is meant for, in your exams you're not going to ask to prove this theorem. What matters is the application. So I'm going to demonstrate the application of this theorem to enhance the understanding. So we have this tangent and we have the chord. Now there is an angle that we're going to build an angle. Okay, we're going to make an angle to come between this tangent. Okay, put a point on this line. So fine. Okay, I want an angle between chord AB and this tangent BC. Okay, so let's put an angle there. Okay, and now let's see what's the size of the angle. We have 51 degrees. Let me make it a bit visible. Okay, let's increase the font to 28. Okay, beautiful. So I can remove this annotation here. Okay, so let's remove this. All right. So now I have this. A little bit. Okay. I want to lock up this. Okay, beautiful. So I have this 52 degrees, and that is the angle here. So that's the angle between the chord AB and this tangent. Now, this angle is formed, if you look at it very well, this angle is formed within the minor segment. This angle B is formed within the minor segment. Take note. This angle is formed within the minor segment. And so the theorem is saying that another angle that is found in the major segment that is alternate to the line AB, which is the chord, we have the same value 52. So what does that mean? What it means, an angle is formed where we have two intersecting lines. When we have two intersecting lines, there's an angle between them. So now we have chord AB. We are going to use this chord AB to build two intersecting lines and ensure that these two lines are meeting on the circumference of the circle on the segment that is alternate to this minor segment, which is the major segment. So we take our segment 2, move it from here to this place, and take it back to here, right? So let's demonstrate that theorem now. Okay, now we have an angle that is formed between this chord BD and chord AD. Now, this second angle is in the major segment. Let's get that angle out. Automatically, do you see what the GeoGebra brought out? The same 52 degrees. And that is what the theorem is saying. Okay, so here we have 52. Here we have 52. So the theorem is saying that these two angles are equal. The angle that is formed in the minor segment cut off by this chord AB will be equal to the other angle in the major segment that is alternate to the chord. So because this chord has cut off two segments, we have the minor and the major. So the part of this circle that is alternate to the chord AB, or that is the other side of chord AB, we also have an angle that measures 52 degrees. That is what the alternate segment theorem is just saying. So guys, I've illustrated this. Anytime you see this, this is actually what it means. And then somebody might be asking, just remember also here, somebody might be asking, what of angle A? Will it also be 52 degrees? No, remember, we are looking at the reference line here is called AB. All right, we look at the angle between the chord and the tangent. So our chord here, out of AD, AB, and BD are all chords, 3 chords. But which of these 3 chords is meeting with the tangent? It is called AB. So this chord AB meets the tangent at point B, and an angle is formed. And this angle formed is in the minor segment. So the alternate segment will be the segment that is alternate to chord AB, the segment that is directly opposite chord AB. And that is why the angle that we have drawn so far will be directly facing chord AB. Look at that. It will be directly facing this chord AB because this chord has something to do with the tangent. This other chord AD, and if you look at another learner may debate that, okay, fine, but chord DB also has something to do with the tangent. Yes, if you look at chord DB, then you should be looking at the angle between this called DB and the tangent, and which segment is opposite to this particular minor segment cut off by chord BD. It is this particular angle here. So if we are having an angle here, theta, for example, then this is the segment that we also, show that angle theta. So guys, I hope this explanation is clear. So when we begin to solve problems that involve the use of this theorem, everything is going to be very clear. So far we have covered the theorem on tangent and radius of a circle, that is the tangent. The radius is perpendicular to the tangent. We have also seen the theorem that establishes the fact that tangents drawn from external points are equal in length. And finally, we looked at the alternate segment theorem. So that is it for today, guys, on tangent. I hope you find it helpful. Don't forget to test your understanding with the quiz and drop your opinion in the comment section. If you enjoyed this video, smash that like button and subscribe to our channel for more engaging math lessons. See you in our next class. This is Math Minders Academy saying goodbye for now.